Good morning. Welcome to this demonstration of a couple of simple experiments of the Sensors and Measurements Lab of the Third Sem Medical Electronics. We have got to this mode because of the pandemic situation, as all of you know. And how do you go about submitting the record and all will be explained later through the Google Classroom. So currently we are trying to demonstrate 5 experiments to you, about which you have also learned in the theory classes. The first set of experiments here are based on the the 3 popular temperature measuring devices called as a thermistor. As you know, it has got negative temperature coefficient of resistance. So then the RTD, which has got the positive temperature coefficient of resistance. Then a thermocouple, which is the passive type of a device that will generate an EMF directly as a function of the applied temperature, probably with a range of few microvolts per degree Celsius as its sensitivity. And the arrangement here is as follows. This is the tub in which we have filled water, and these are the devices that we have inserted already. So this particular device is what is called as a thermistor, whose starting value, as you can see, is somewhere around 1.358 kilo ohm. You will see how that drastically falls to a low value as we apply the temperature to this device. The heater is yet to be switched on, so this is the this is the resistance around this temperature, which could be around say 22 degrees Celsius. Then the thermocouple, as you can see here, is showing 0 millivolts because maybe there is a fraction of microvolt in this multimeter that is set in voltage mode. I may not be able to go to the microvolt range. So, but it is showing 0, but actually there will be a very small value of microvolts in that. We'll forget that for a while. And this is RTD, which is exhibiting around 109 ohm. We have told you that platinum is a very widely used material as a choice for the RTD. So this is a PRTD. This is actual device. This was already shown to you in the class. This is the way an RTD looks like for usually laboratory grade. And industrial RTD will be even more sophisticated and rugged. So this is the steel covering sheath. So it is at this particular tip we have the platinum as a sensing material, and as you can see there are a couple of wires coming out of it that goes to the multimeter, which is trying to measure the resistance of this particular device. So the starting values are 1.35 K at this temperature, which could be around say 22 degrees Celsius. This is showing 0 millivolts at that temperature. This is showing approximately 110 ohm. At 0 degree it should be able to show 100, but because this is above that, it is showing some value. So now once I switch on the heater, you will see that this resistance will fall because thermistor has NTC, and this resistance will increase at a lower rate compared to the thermistor, but however it is PTC, so therefore the resistance is going to increase, and this thermocouple EMF will also gradually increase as a function of this, but compared to the changes at which these two happen, this will be little less because that's the value of the thermocouple sensitivity. So now let me switch on the heater and demonstrate how this decreases, this increases, and this increases for you to cross check what was taught in the theory, and then we will tell about how do we go about writing the record, etc. for the sake of submission and evaluation. Maybe by Monday or Tuesday we will tell you that, right? So now let me switch on the heater. It will take a while. So as you know, all temperature measuring instruments are first order instruments. They will have their own time constant values. You can see that it will not suddenly drop, or it will not suddenly increase, or this will also not suddenly increase. It will take a time for the temperature also to be set up in this particular medium. But just wait for a while. We will show you how this drops and this changes as a function of the temperature. We will share the readings with you so that you can prepare the laboratory record and submit it to the teacher. So this fellow is already started to fall. Why? Because thermistor is highly sensitive compared to this. See, this is slightly increasing, and this will take a while to increase. Now of course it is changing, but it is in a microvolt range. You will see that also increasing as a function of the temperature. Hope you can notice the increase in this, decrease in this. So now it is showing 0.1 millivolt at that temperature. It will be difficult for me to read out the temperature and then correlate these things. We'll share the readings later, but just get a feel of the experiment because it's a demonstration of the setup what we have to measure temperature. Maybe we'll show it for a minute or so for you to appreciate the drop in this and increases in these two. See, it has gone to 0.3 millivolt now. will even go much below a thermistor, they're highly sensitive. Large change in resistance for temperature is what I have told you. That is what is happening. It has come down to 0.97 K from 1.3 K. This is a small increase. From 110 it has only gone to 114 ohms. This is also a small increase, which is gone to 0.5 millivolt. Yeah. So hope you got a feel of the experiment. We'll share the readings of all the 3 experiments for the other purpose intended. Yeah, so this is the second experiment we are demonstrating, which is about the strain gauges. We have taught you that resistance changes as a function of temperature, and also the strain that is being created, which is the change in length to the original length, what we call as epsilon in microstrain. So actually this is a small setup. As you can see here, it's called as a double-ended cantilever beam. But one end is called as a fixed end and the other is called as a free end. So this end cannot move, and if you apply force over this particular platform or a pressure over this, so there will be a deflection of this downwards. But see, always in a fixed cantilever beam like this, when you apply an unknown quantity here, the deflection is maximum here. So I can measure the force that is being applied using a displacement transducer that is connected here, and obviously because this is a fixed end, the strain created here will be very maximum. Yeah, so that's about this particular double-ended cantilever beam, which is fixed at one end and which is free to move at the other end. So this is where we apply the unknown force at the load, and you have the 4 strain gauges that are bonded onto this in the form of a bridge circuit, right? So that's about this setup, and hope you got an idea of how it is happening. So when you apply force here, so there is a strain created here that is maximum here. So I am unable to show the strain gauges that are mounted onto this, but using the regular procedure of cementing and bonding. So you have the gauges that are mounted to this particular fixed end, and now that is going to this particular black box, which has got that bridge circuit that we saw in one of the worked example, then some couple of amplifiers and so on and so forth. So what you see on the digital multimeter here is the output of that particular voltage, right? So probably when you come back to the college in the next semester, we can just cut it open and show what is there inside this particular box. But for a while, please understand that when you apply a force on this, the strain gauge will get strained, leading to delta R changes in all the 4 gauges here. That goes to this particular box, which has got a Wheatstone bridge like a circuit with an DC excitation. So then some amplifier etc. will be there inside that. So the differential output of the bridge is going to this particular multimeter that is showing. So now there is no force that is being applied. This is showing 17.2 millivolt because the bridge is not perfectly balanced. It is to show this that I have not made the zero adjustment in this, but all these instruments will have what is called as a Tare controller zero adjustment, using which you can get zero output when there is no load being applied, right? So you can call it as an offset, because I have not done that intentionally, because I wanted to show that there will always be some kind of an unbalance in the bridge circuit, giving you a small DC voltage when there is no load. So now if I apply load to this, you can see that increasing because this particular device has positive coefficient. So now it is 17.2 millivolt. I'll apply a very small weight here. You can see that increasing to some extent. It is just 0.6 increase. So if I apply the next weight, that will further increase. It has gone to around 18. That will be very linear now. Probably when you plot it and try to find out what is the sensitivity of how many millivolt for 1 gram of weight, you will be able to appreciate the sensitivity of this device. So let me go on putting weights like this. So it is increasing. Yeah. Now it is around 20.5. Let me apply a little larger weight. 24. It will take some time to settle, because all these are second order instruments typically. Now let me apply little larger weights. So same principle is used when you go and stand on a weighing machine that shows up your weight as 50, 60, 70 kg or whatever. The same concept is used, but this will be calibrated in terms of your weight, which we have not done, of course, because my intention is to give a basic demo of the strain gauge setup that will show you so many millivolts for the given weight that is being applied here. See, now notice the reading. it is 76.7, right? Now let me apply another load. So I'm trying to load it. It has gone to some other value, 84.9. Now if I take it back, if it gives me the earlier value, 76.4 it was, now it is slightly different. This is what we call as hysteresis. So when you load the particular devices, the voltages was increasing. When you now try to unload the weights, if it does not follow the initial value, so there is a small hysteresis. Hysteresis is a part and parcel of all these mechanical devices that will have some kind of a deflection like this. So that we learned in the theory class, right? So that's about this particular strain gauge setup. The gauges are fixed at the fixed end, and I'm applying load here, increasing or decreasing. So this black box has all the electronic circuitry inside, ultimately to give me an output voltage, which is a function of the load applied, right? So that's about this experiment. Yeah. So in the class we discussed about what are called as the zero order, first order and second order systems based on a generalized mathematical model. And later on we study what is called as the dynamic response or the frequency response of the particular devices, especially what are called as the step responses, to understand how does a zero, first and second order behave when you apply a certain step input. But because it's very difficult for me to show the step response of a the thermocouple experiment for that matter, which is a first order instrument. So what we have done is we have made an RC circuit which behaves as a first order circuit. See, the concept of zero, first and second order are very true for all systems for that matter. It could be a mechanical system, or it could be an electrical system, or it could be even higher order systems also. So here what we are trying to do here, as you can see in this particular figure, I am applying a signal generator to an RC circuit like this, where you have an R1, R2 and C1 in series. I am taking the output between this particular series combination of R and C, which tries to behave as a first order instrument. So now to this particular instrument, if you apply step input that is at some zero value and suddenly goes to the final value, the device will take some time to respond, and we have defined time constant as the time it takes to reach 63.3% of the final value. So all those things we have taught you in the theory, and this is an expression for the output, which is E out of t is 1 minus half of e power minus t by 0.002 based on the value of R1 and R2 and C that I am using here. This sheet will be shared with you, no need to worry about it, but please be convinced that I have made an RC circuit which will behave as a first order instrument. Now I would like to show how a first order instrument behaves for a step input, the theory of which you are already familiar with. But here I can either have a voltage that is zero, then apply a step input, but to make things easy for myself, so what I have done here is that I am using a function generator that is continuously giving a square wave. That means you are repeatedly applying step input, as simple as that. For example, it is at some low value, suddenly it goes to a high value, again drops, and in the next cycle again that is being applied. So I am continuously applying step inputs because I am operating this at a certain frequency, but the concept will remain the same. It is in the class we showed you how a system will respond for one step input, but if I repeatedly or continuously apply the step inputs, the same thing keeps happening. So that's what I have shown here. So I have chosen some value of R here, and now this is a decayed capacitance box whose value will be changed now. When you change the value of C, the time constant will change. But now this is almost at a zero value, so you can see that for a step input the output is also a step output, but for a small curve, if you can notice here, that is because of some this capacitance, which could be nanofarad, picofarad. Now let me increase the value of C, just make a notice of what happens to this particular waveform. Now let me add something like 10 kpf, which is 0.01 microfarad. Can you see that? Now with the inclusion of C, it is not able to immediately go to the final value, but it is taking some time to go to that value. So therefore, that's how we define the time constant. So if I keep increasing the value of C, it will become more sluggish and take even more time to go to the final value, right? So now it is even more sluggish, right? Hope you can make a sense of it. Yeah. So let me further increase the value of C. It becomes even slow, right? So that means with the increasing value of C, the RC time constant of the circuit will increase. The same thing can happen with your thermometer also, as a function of time constant. The time it takes to respond to any step input will be changing, right? So now let me again go back to the zero value of capacitance. For a step input, the output is almost a step output, but as I include the value of C, it will become little sluggish and takes its own, like the capacitance, being charging exponentially or discharging exponentially is happening here. So that is a very property of any first order system. It is not a mechanical system though, but I have been able to make an RC circuit that will behave as a first order instrument, and hope you are able to appreciate the step response of a first order instrument, right? So this is for one time constant value, this is for a different time constant value. If I increase the time constant to a very large value, it will become very, very slow to respond. In fact, it can never reach the final value at all, because the time constant is very large, or given a time, it may take a day or so to reach the final value, right? Hope you got a feel of how a first order system will behave for a step input, right? We have shown a similar response in the class also. Same thing is being shown here, because my intention is to demonstrate how a first order system behave for a step input. So with this, let me move on to the second order system now. Now let me demonstrate how a second order system behaves for a step input. So like what we did for a first order instrument, we have a similar RLC circuit here. So the circuit that you can see here, that has got an inductor in series with a resistor and then a capacitor here, that is being applied with a continuous square wave input that will as I told you, work as a repeated step input, and I am taking the output across a particular capacitor. So this now becomes a second order system. I have given the example of a weighing scale in the class, that is a second order system. Even this RLC series circuit, if you derive using the suitable current and voltage equations, you will get an expression like this, which is A2 d square yt by dt square plus A1 dyt by dt plus A0 y into A into u of t, where u of t is the step input. And as you know, we define what is called as alpha, the Jeeting factor, then the damping coefficient, then the damped frequency, and then omega naught as a natural frequency. And for this particular setup, we have got 1 by root of LC as the natural frequency of oscillation, and zeta is given by R by 2 into square root of C by L. So I am assuming the value of L to be say 100 millihenry. I am sharing this sheet with you later, so no need to worry if you can't understand the whole of it. Once you go through this, you should be able to appreciate the matching of this RLC series circuit with the second order system that we have discussed. Anyway, just get me that. By fixing the value of L to be 100 millihenry and C to be 0.01 microfarad, we get a natural frequency of omega naught to be around 31.62 radians per second, which in frequency becomes 5 kilohertz. Now I'll keep all these constant. I just vary the value of R. So I'm trying to demonstrate how does the second order system behave when you vary the value of zeta. And again, the values of zeta, omega, and all those things will be shared with you. So you will be building a tabular column like this, or we will build a tabular column and share with you. Ultimately, as you vary the value of damping factor from say 0.01 to 5, by varying the resistance value, you will have different peak overshoot coming or undershoot coming, and the number of oscillations will die down as you increase the value of zeta. So this is the system I am trying to explain, which already has been taught to you. At a very low value of zeta, something around 0.02, you will see a lot of oscillations like this, which will take their own sweet time to settle. And as you keep increasing the value of zeta, in this case by increasing the value of resistance, the oscillations will die down, and for a very large value of resistance, it will become what is called as a overdamped case, right? We know zeta is very less, is a underdamped case. Zeta approximately equals to 1 or 0.9 will give us what is called as a critically damped system. When zeta is very large, it will give an overdamped system, and the step response for a overdamped system with zeta being very large will be close to like a first order system. In fact, that can fool you, that as already I have mentioned, right? So now let me demonstrate how will the circuit behave for different values for RLC components. L and C are fixed, and I am just varying the value of R ultimately to aim to change the value of zeta, the damping coefficient here, and you can see the response here. So I think this is now somewhere around 300 ohms, and as you can see here, this is step input I had applied, but you can see the peak overshoot, then undershoot, then it will take its own sweet time to settle, right? So that's a very classic example of a second order system in which you will see a lot of oscillations like this whenever you apply the value of R is being changed so as to change the value of zeta, L and C being fixed. Now let me reduce further R further. You can see that the oscillations will increase because I am trying to decrease the dampings. Look at this. R is somewhere around say 100 ohm, and you can see a lot of oscillations here, and in fact it is not at all settling at the final value. Before it is settling at the final value and applying a negative step, and again the oscillations will begin, right? So this is at a value of zeta that is very low, maybe around 0.02 or whatever. So if I increase the value of resistance, I am trying to essentially increase the value of zeta, or the damping has been increased, so then you can see how the oscillations will die down. See that? Now R is somewhere around 400 ohm. You can see that there are only 1, 2, 3, 4, 5 oscillations here. If I increase the value of R further, the oscillations will further die down. See? Now I kept this together 900 ohms. You can see there are only 1, 2, 3 oscillations, and immediately we'll set at the final value. So that's how the step response of a second order system will change based on the value of the jetting factor, damping factor of the zeta. Now let me further increase the value of R. You can see that there is only one overshoot now because the zeta is quite large. If I further increase the value of R, so that will become an overdamped case. As you can see now, it will almost look like a the step response of a first order system because the value of zeta is very large. That was already told in the beginning. So that's it, as simple as this. By varying the value of zeta, you can make the circuit response to behave like a second order system, right? So this is for an underdamped case. I'm increasing the damping, so the oscillations will reduce. Yeah, this is very nice. Look at this. These are I have 2, 3 oscillations. Then if I increase the value of R, the oscillations have come down to 1. If I increase the value of zeta to a very large value, it is almost behaving like a first order system. Now with this value of R and the response you are trying to get, it becomes a overdamped second order system. This will be an underdamped case, right? Maybe somewhere here I'll get the critically damped case where it will just make one oscillation and then stop there. So that becomes a critically damped case, right? Yeah, hope you got a feel of it. We are going to share the readings with you and give the further instructions. Probably by the end of next week, we'll get back to you with some instructions about how do you go about submitting and then also take a quiz later towards the lab component evaluation of the SAM course, right? With best wishes. And I'll be failing in my duties if I don't thank my colleagues Vinay Rao here and Pandran Kulkarni who really helped me to make the whole setup. And of course, Anil for the wonderful video recording. Thank you, Anil.
Thank you, sir.
Similarly,